Hi, good morning, everyone. This is Ali Rasek. I'm a structural engineer at HDR, and today is July 23rd. This is a makeup session for the one session that we missed or I had to travel. Therefore, participation is not mandatory, and I just try to quickly continue with the course to finish the a structural earthquake design. And yeah, hopefully I'm audible, or maybe I'm not. No, am I audible? I'm connected to this. Should be, but it doesn't show here. Can somebody send a text message, say if you hear me or you don't, or tell me?
Yeah, we can hear you.
Okay, yeah, I don't know, but sometimes it's out. No, it's it. Okay, thanks a lot. Thank you. And yeah, so there was an internet shutdown right now at my office, which was very, very unusual. So I connected to my cell phone internet. And that's why I was delayed for a few minutes until I connected to the hotspot, etc. Let's quickly review what we want to do. Thursday is a very important, Friday is a very important day. 26th July, I will be at UVic, and these teams will present. Team 6 already said that they want to be first, which is okay. We can start with Team 6, and that just on volunteer basis, whoever is ready earlier or later, they can do in that order until the end of that session, which is about 3 hours. I anticipate 25 minutes per team for presentation plus questions, and about 5 minutes rest per team. Plus, minus, or it could be plus because it will finish in 2.5 hours with this scheme. So everything is good. I think I am recording. Yeah. And also start recording, which means that we are recording. Okay. Let's jump on the slideshow and quickly go through a few of them as if it's a conference presentation. And we have a good number of people already here. Oh, question about the quiz? No, because as I said, I made it voluntary. So it's like, yeah, whoever wants to stay can stay. Otherwise, I record the session and I will upload it. One more message. No, nothing more. Okay, that's the one. Yeah, then there is no quiz today. I just want to, walk you through this slideshow and hopefully the next one. Alrighty, let's continue. Everything is functioning. Hopefully my hotspot doesn't disconnect or anything. Last week I talked about this 3-story building example in 3D. There's a SAP 2000 model for this, and it's already uploaded to the Brightspace, or otherwise I will upload it or make it visible. And today we focus on this model, or I think we already went through this quite a bit with faster pace. Yeah, I think that we almost finished this one. No, we started, we described it, so let's describe it one more time. So basically 3-story building, concentric bracing system, and in both directions. Supposedly using National Building Code of Canada 2020 for the loading, earthquake loading, and CSA S16 2019 for the steel design. It's going to be a moderately ductile chevron brace frame for seismic force resisting system and effective seismic force use, and also the response spectrum analysis. The mass, yeah, as we said, masses are important, so make sure that the mass is either accounted for as nodal masses at the nodes or as mass of the parts, such as frame members or shell members. Or if you don't want to be bothered by the shell stiffness, maybe make it zero stiffness, but give it a mass, because dynamic analysis is related to the mass when you want to do, especially the RSA, which is the true dynamic analysis. If you do equivalent lateral load, equivalent static method, then mass is not very important. But in either way, you need the weight, because weight should be combined in terms of load combination. It should be combined with earthquake effects. And yeah, remember that we described the model in here and in SAP 2000. Let me see if I can open the model in SAP 2000. This is for module number 8, 3-story building example. Let's see if this opens, and with the current version of SAP that I have. Message. Maybe I cannot use the licenses because I'm connected through my cell phone hotspot. Yeah. Okay. Luckily, this was a voluntary session. Okay, things are not working as we want them, so my apologies. But either way, I will walk you through the model. I'm gonna click too many times. So I previously described the SAP model, and there are 150 millimeter. So the section for beams are W section for beams and columns. And it's called initial because you can do iterations, you can update the sections during design, and the braces are HSS. And the SAP 2000 model, for SAP 2000 model, the 150 millimeter concrete slabs are considered, and the 25 millimeter slab for the roof, connecting all points in each level using a diaphragm type of constraint, like all nodes move together as if there's a rigid floor, which is a good assumption with concrete slab. So there will be slight flexibility, but it's pretty much a rigid slab. Add 25% of snow load to roof for load combination. Using 1.5 kilopascal for snow, total roof area is 648 square meter, and therefore the total snow load would be 243 kilonewtons. For seismic cases, add as weight to roof joints 243 divided by 35 nodes or joints, 7 kilonewtons per joint for weight of the snow. And for snow load case, add an area pressure at 1.5 kilopascal to the roof level. And that's it. Analysis model, other stuff to be considered, add 50% of live load and partition to the first two floors. For partition, use 1 kilopascal for partitions. And again, we can divide it between all 35 joints in each floor. And for pressure, again, we have the pressure value, the full pressure value we add to the area. So one is for mass in order to be able to run the RSA, and the other consideration is for load and weight. I wish I could open that SAP 2000 to show you. Try one more time. I should be under VPN, so I'm surprised, yeah, because there is VPN, so SAP 2000 should work just fine. But no. Okay. Sorry about this issue, unusual issue at our office. And so the more modeling considerations to check seismic weight. First, compute the dead load case before you add additional masses, add masses, and then apply a horizontal acceleration case scale to 1. Calculate the best shear should match what you calculated by hand. So this is basically, if you want to do a sanity check, you can do this, or you just can carefully add up all the masses you added to the nodes and sum them up to make sure it sums up to the total masses that you want to add at each floor to account for dead load and part of the live load and part of the snow load. Since the requirements from National Building Code of Canada is that the seismic force resisting system must be designed to carry 100% of the lateral loads, we need to change the frame condition to pins, otherwise there will be moment frame action. So basically what we are saying here is that we are designing it so that it's bracing only, and therefore in the modeling we should also consider bracing only. If part of the lateral force goes through the moment frame, then then maybe you under-design your bracing, while the intention was that we have a bracing only. Therefore, in your modeling, you should be careful that basically you model what you want to have, which is non-moment carrying frame for lateral load, which means pinned connection at the ends of the members, beam and column members. And besides that, you have the bracing that carries the lateral load. So this applies to beams and braces. Also braces, we don't want them to carry moment. They are not designed for moment. They only carry axial load. So you can release ends. I wish I could show it to you in SAP 2000, but you can find that command, or maybe you already know about that. This is something to be careful about, that wherever you don't want the moments, then you release the ends so that there is no end moments in those members. In this case, in no beam or column or brace, we want end moments. This is done in SAP 2000 by changing the frame element and fixity or release. So this is a very important feature, and you should be careful in your modeling. Modeling considerations, more of them. Actual diaphragms would likely be composite, a steel deck, concrete slab. Okay, this could be modeled with area elements, which could be done in your ETABS program, but maybe this is less of interest to me. But if you want to add them in ETABS and even design them in ETABS, you can do that. Load cases that are considered, modal load case, we normally do that to determine the periods and shapes and primary mode shapes of the structure for RSA, and dead load needed for final load combinations, a static, use National Building Code of Canada 2020 effective lateral force, which includes 10% accidental torsion. Response spectrum, again, include 10% accidental torsion, and the RSA torsion will be computed as additional resulting forces. So the load combinations that we are interested in, per the table that I showed you in the National Building Code of Canada, is dead plus earthquake, which is the most important, and in the snow regions, 25% of snow should be added as load combination, and 50% of the live load should be also considered. So this is separate from the amount of snow or amount of live load that contribute to the mass. So those are two separate topics. So those are the static cases and RSA cases accordingly that are built in the model. And I intended to show that to you, but you can open it yourself and look into the model. The total seismic weight turned out to be 8,380 kilonewtons. For period, you could look at the modal analysis results, but the code also gave you this equation for braced frames based on the height of the system. And you can calculate 0.3 second, which is not as surprising because for 3-story, for very quick back of envelope, you do 0.1 second per story. So that's what you expect to see. For 3-story, should be close to 0.3 seconds. And then from the spectral acceleration at 0.3 second, you read 1.26 G from your spectral acceleration plot. Then you go to the still code that I showed you last week, and you read for moderately ductile brace frames, use modification factor for ductility, which is 3, and modification factor for overstrength, which is 1.3, and importance factor is regular building, and modification for higher modes was not there because it's only 3 stories, so I didn't even think about it. And then you can basically calculate your total base shear. TA multiplied by the MV and IE and weight, and then reduced by the 2 modification factors, reduction factors that we have. So equivalent static method or equivalent static method, the program can also generate the lateral load for you. So you can practice that or try that one. Just bring up the form for National Building Code of Canada. This is done for 2015, but I assume that the newer versions might have 2020 as well. And you just fill up the form and the program calculates the pattern of the lateral load for you. For such a short building, I might even do it by hand calculation to be confident that the program properly applies the total load. But then you can also after the analysis, you can double check the base shear to make sure that there is no mistake and all the lateral loads sum up to base shear. A static analysis results. So for base shear that we calculated to be about this value, 2,570 kilonewtons, the results are the same for code per analysis period. And both in X and Y directions, you can double check. The code period are all less than 0.5 seconds, therefore have same design spectral acceleration. So basically, I think this relates to the fact that we don't need to add any additional load on the top floor for the shorter buildings. Again, to account for higher modes, which we don't have it in a relatively shorter building. The deflection is read to be 8 millimeter, and the drift for the whole system is about 0.2%. And so that's what you read from the program. But because it's like reduced, remember that for forces, we use the reduction factors, but for deflections, we shouldn't really use the reduction factor. Therefore, that's a reminder here to increase your deflection by the same modification factors by using the reverse of RD and RO and also importance factor. We don't want importance factor to be built in the deflection as well. So we apply it in a reverse manner and we read 0.8% deflection, which is less than 2.5%, which is by the code. That's what the limit that the code gives us. And we need to check again with final load combinations, check the drift again with final load combinations. We can also look at the results of the modal analysis. We have a 3D model, so the mode shapes are 3D. As you see here, even on the first mode, the structure is both deflecting and rotating, which is what we expect. For all three modes, where we have such a combination of deflection to both directions and also rotation. So all three modes are almost mixed mode. Mode 2 looks like it's only or dominantly lateral movement. So we have torsional modes as well, and as you see, if we call them the real first mode had an even greater period. It was 0.37 versus 0.3, which we calculated using the code equation, but same order. Maybe this is because there is some softness in rotation. If this was like, well, if you didn't have this cutout, maybe it was stiffer and it was even closer to 0.3. Mode shapes, you can watch them. I encourage you to do that. Open the models, you can investigate the result of each load case to kind of understand each major primary mode of the deflection of the system. And mass participation, that's what we previously discussed, that we look at the mass participation to really understand what is the dominant deflection, the dominant feature in that mode. And as you see, like here, mode 1, the description, we found out that it's dominantly Y direction. Why? Because if you come here, you see that there is a big jump in the Y modal mass participation. So, which means that most of the mass really moved in Y direction. So unlike what it appeared to be, this one was dominantly moving in Y direction, which is this direction. although we can see the rotation as well, but it's dominantly moving in Y direction, and the proof is basically this. Uy suddenly jumped from 0 to 0.83 out of 1, so it's like 83%. Mode 2 is dominantly displacement in X direction. Why? Because the modal mass participation in the X direction jumped from a relatively small value to a large value. And the third mode is mostly rotation, because there is not much change in in the mass participation in the X direction and not much change in the Y direction. If you calculate the rotational mass, that would be a big jump there that you can do by hand calculation. But best case, maybe probably by inspecting the picture here, is that it's majorly rotating. So first mode, maybe unlike what I initially said, now that we looked at the mass participation factors, I can say that in first mode, it dominantly moves in this direction, which is Y. In second mode, it dominantly moves in this direction, which is X. And in the third mode, it dominantly rotates. Again, mode 4 adds more to the Y modal mass participation factor, modal mass in a way, increasing it to 99%. And then mode number 5 increases the X direction deflection to 99%. And if you go to mode 6, then already in every direction you have captured 99% of the mass. However, we said 90% is good enough. So here you see that going up to mode number 3, you have captured 90% of the mass in each direction. And therefore, for RSA, it's good enough to use only 3 modes. But it doesn't take analysis time, computation time to really go to 6 or even more. Continuing with the response spectrum analysis, you can inspect those in the model. The response spectrum function could be automatically generated in the program based on National Building Code of Canada 2020. And you type in the hazard values that you read from NRCAN website. I previously showed that to you. And you select the site class, and the program creates the plot for you. Or you can manually type in this table here, period versus acceleration. Either way. Yeah, I normally prefer not to use the forms and prefer to create this table separately, maybe in Excel, so that I can verify it and then copy that Excel table into this form. I prefer that rather than what SAP 2000 creates automatically. Then setup for response spectrum analysis. So define response spectrum load case and diaphragm eccentricity ratio. You can enter that one. The scale factor, like in this model, this particular model, and if I want to do it, I apply all the reduction factors and then type in those values into this table. But however, like in this model that was prepared by others, there are values for the spectral accelerations are typed in here or generated here. And therefore, the G value And also the reduction factors were implemented through the scale factor. So we should make sure that these are accounted for one way or other. Can add like spectral accelerations in multiple directions and can select the directional combination method. As we said, for directional combination, SRSS is good enough. However, for every single direction, maybe people prefer CQC because it works better when the periods are spaced together, they are close to each other. Yeah, you can change or play with either one of these options. I encourage you, now that you are learning, play with it so that you can see the difference, or you can see that there is no difference. And modal damping should be implemented. Here, the modal damping was set to be 5% for every mode. It can be same for every mode, or it can vary by mode, or you can use the Rayleigh damping, which basically increases the damping for higher modes. That's what it is to creating this load case for RSA. And yeah, looking at the results, base shear is 2295, which is dividing it by the total base shear that you expected. It's at 89%. That's what we kind of expect because we used only 3 modes, which basically uses, we already said that 3 modes will use up to 90% of the mass of the system. So that's basically already planned for. Deflections from this solution. First, Storey has the largest displacement of 7.3 millimeter, and the drift, total drift is again 0.8%, same as equivalent static. Base shear in the other direction was also close to 90%, and the deflection in Y direction was about 1%, which is still okay. Design of a brace bay. For design forces, we now need to use the load combination. We will look at the brace bay on the bottom face of the building. In Y equal to -12 meter wall, we will use the response spectrum case in the X direction. We read the load from response spectrum case, and we will do 2 load cases as mentioned previously. One RSA only, and one RSA plus dead load plus live load and part of the snow load. So principal, that's the way the National Building Code divides it, like principal or principal plus companion. To me, it looks like obviously number 2 is larger, so it should control. We will add the accidental torsion separately. So accidental torsion will be accounted for separately. So brace axial forces, the maximum values for each load cases. And so this is the dead load plus earthquake load plus half of the live load and a quarter of the snow load, obviously the larger one. Dead plus earthquake, obviously slightly lower, and the torsion effect only, that is done separately. Design approach. For braces on the first story, need to add the notional loads, 0.5% of the gravity load. Don't forget about that one. That's the way we account for accidental eccentricity. of the members if they are not really fully vertical. We will use the seismic wave check results and then multiply them. We read the axial load and then multiply them by basically 0.5%. For this brace, we added another 12 kilonewtons. So we had 803 coming from this, 62 coming from the accidental torsion, and 12 kilonewton because of the like 0.5%, what do they call it, non-plumbness, meaning that it's not exactly vertical. So that comes from non-plumbness. The total axial load could be 877 as we combine these load cases. As we said, for bracing, we can directly go to the handbook, and the length is 5,000 millimeter, K is 1 for pin, and we can find different alternatives that meet our demand in compression or tension. In this case, we found HSS, 2 HSSs which were close, and we used we should use the one with a smaller area. Yeah, here is the area, or the code even tells you weight per unit length to be optimal. We use the one with a smaller area. And when we use this, then the compression capacity is 1010, as we read from the code, and the tension capacity is 1650. Now we go through the same exercise about the probable resistance. We illustrated that with a shorter example last time. For tension, probable tension, we should use RYFY instead of PFY. And there is a minimum for that, which was 460. Therefore, the probable tension is 2406 kilonewton, and this is the area, 5230 for that member. For compression, probable compression capacity, again, we had a procedure which will result in 1539 kilonewtons probable compression capacity. And for post-buckling capacity, again, we had a procedure which resulted in 481 kilonewtons. So we have the probable tension capacity, probable compression capacity, and probable post-buckling capacity. And we can use limit of RDRO equal to 1.3. Recheck RSA case using RDRO 1.3, and the brace forces are 2509 kilonewton. As you see, like we wanted to basically double check the ceiling that the code has provided for using the capacity protection. The code says you don't need to go below this value, and therefore we first check the ceiling, which was 2509. It says the code says you don't need to design for more than 2509 kilonewtons. But we were at 2406, so we are lower than what the code asked for. That's why we use the probable, which is smaller, probable tension capacity. We need to update our model. Initially used this value, this HSS in the model, 203 by 203 by 604, while we are now designing for 178 by 178 by 7.9. We can go through those iterations. periods slightly changed. The structure is stiffer, so we are getting closer to what the code really suggested, which was 0.3 seconds period. And we read the base shear again, so maybe this iteration should be done a couple of times until we have the final values. And the deflection is still acceptable. Axial brace force is now only 800 kilonewtons. Forces and displacements are nearly the same, but with the smaller outside sections, we ended up with larger thicknesses and then larger areas, and we have larger probable resistance and a stiffer structure. So that's basically the loop that we previously said, that when you use larger members, then you end up with attracting more earthquake load, and then maybe you need even a larger member again. Like, that's the thing with earthquake engineering, that making it stronger causes it to attract more load in a way. Need to design connections, columns and beams, and rest of the structure for the capacity protected load, but you can do that in the SAP 2000. Special considerations. We have some special considerations in class 27.5.2.4. If we have a class 1 section beam and our building do not exceed 4 stories, we can take a brace force of 0.6 T probable. To be a class 1 section, need to meet limits from table 2, and therefore we can use W section 250 multiplied by 89. And you can consider that if that reduces the T probable, or the T probable that practically should be used. Our capacity design force is now governed by comparison 1539. And what does that mean? Before, we had capacity design force of 2.7, now 1.8, and can reduce loads on the foundation. So going through this procedure, we ended up with smaller capacity design. So we always want to use as many ceilings as we can on the capacity design, because as I said previously, that procedure, capacity design procedure, while it is sensible, it can end up with huge forces. And therefore we look at the caps, basically, that the code provide for capacity design. That's it. I went through this as if it's a conference paper, and unfortunately I couldn't open the sub 2000, but that is fine. This is only a makeup class, and we want to do as many slideshows as we can. We did 8.3, 8.4, 8.5 pushover. Yeah, pushover is also super important. Let's see, as if I'm presenting a paper on pushover analysis. Just I will read through in 20 minutes or 25 minutes, and then we are at the end of the steel design. Yeah, and then maybe I do same next Tuesday for concrete, so that I don't need to teach during the visits. What is pushover analysis? We previously told you guys what pushover analysis is, like slightly pushing a structure to one side and letting the plasticity happen in the members. For a steel structure design, plasticity that we desire for is creating the plastic hinges in seismic force resisting members. We apply the static and weight load because the loads, different loads combine with each other. And then we apply the lateral force gradually with a pattern which could be like uniform pattern or a triangular pattern, or enough of course say check both of them. We track forces with capacity of the members, and we create hinges when and where they should happen. And at the end, we build up a load displacement plot, which could be used for design, more advanced design, but it has a value per se because when you go through the process, you will see which members are yielding first, which your intention is that your seismic force assisting system to yield and everything else remain capacity protected. So even going through this procedure and not using the end product, which is that force displacement curve, is still valuable. How to do it in SAP 2000 for a 5-story building? I shared the model with you, and I walk you through it right now. So the model from a previous lecture, I copied it from the previous lecturers. I was allowed to use the material from previous lecturers, and I slightly modified it. All joints are retained in y direction, so we are not studying the y direction, which is towards the surface. Base joints are restrained in all directions. These are the base joints and shown from the side. Every other joint is restrained in the y direction because we are not studying the y direction. For lateral load pattern, we have used the National Building Code load pattern, which is pretty much triangular. And we can use a scale factor to increase and reduce and increase the base shear until the structure fades. The initial sizing was done for moderately ductile structure, with concentric brace, which the code allows for RD multiplied by RO being 3.9. And so this is the design structure, and with the full applied load, we can see the deflection and forces. Design base shear replicates to be 1261, which is okay. And however, remember that this is reduced value. And when you want to check the deflections, you should basically multiply the deflections you are reading from the model by the factor 3.9, and also the reverse of the importance factor. And deflection is 217 millimeter for this structure. Target displacement for pushover analysis is about 50% more. So we want to see what happens to the structure if the structure moves 50% more than what we think it's like it's earthquake deflection. Again, I want to show you like the model on the left. If you look at the deflection, it's 55 millimeter, which means that the reduction factor is applied, and then if you apply the reverse of the reduction factor, which is almost 4, you get to the full displacement. So always be aware of that. Either don't use reduction factor in your model for deflection, or reverse it. multiply the deflections you're reading by the reduction factor. Plastic hinges, the program gives you a tool, the SAP 2000 gives you a tool for applying the plastic hinges. You can always assign hinges to your frames. And then when you choose this, there's a form to fill up and add the hinge to the structure. And so basically the best description of plastic hinge is given in ASCE 41. The latest update is 2017. So basically ASCE 41, that's the best code for defining the plastic hinges. And for braces, that's all we are saying. Like in the braces, in tension, we want them to be like middle of the length. That's for braces in the tension. And yeah, so in this form, again, we emphasize that we want to use ASCE 41. And which table in ASCE 41? The relevant table, steel braces axiom. Easy to find out, or keep this slideshow for your reference, future reference. Then the program applies the plastic hinges at the mid-length for tension. And the member is in tension, or even in compression, it can bend and have a plastic hinge at the middle length of the bracing. Now check adjust the hinges. Again, you go to the menu and you go to the hinge properties and convert. You can even convert from auto to user defined to be able to override properties. You can do that. And then you can modify or show hinge properties. And you can adjust the TR and CR that you calculated, like your own hand calculation, you can put it in there, or just use whatever the program or ASCE 41 has used. In this case, the creator modified those values. Basically, yeah, easy to follow. And the type of analysis in SAP 2000 is basically more about training or quick training on how to use SAP 2000 for a pushover analysis. And pushover analysis was more about a static analysis where you increase the load. So it's multi-step static. That's the type of the analysis that you are using. And it's a nonlinear because the plastic hinges are created. The loads that you apply is the basically the gravity load and plus the lateral load. Both of them are applied. Load pattern dead plus gravity save only final state as a starting point for pushover analysis. This could be done in as nonlinear multi-step, except if you are confident that a static doesn't create really any nonlinearity. Then you have, so that was case one for gravity. Then you create your second step, which is the lateral load. And you ask the program to start from the gravity case and continue a nonlinear multi-step analysis into pushover. You can ask the program to account for P delta or not account for P delta. So if you are using P delta and the outcome doesn't make sense, maybe you can turn off P delta and get the results and try to guess if P delta has caused some issues. But generally, yeah, for large deflections, we expect P delta effect, and therefore, for the final product, P delta should be activated. And we can note down the results from multiple states. So multi-step static nonlinear P delta continue from a state at the end of nonlinear case, because gravity should have been already done. And then you apply the lateral force pattern, which was based on National Building Code of Canada, and you continue to twice as much. So basically, your target displacement was 50% more than the dynamic deflection, and you kind of expected the load to go twice as much, but maybe it could go even more. You can go three times as much and just continue observing the deflections until it reaches the target displacement. So this factor doesn't matter. In this case, twice as much was deemed enough. Here, yeah, we modified show. We clicked on modify show, and then we basically told the program how many time steps, how many steps of the results should be saved. Save 100 states, and specify maximum 100. So the program quits if it doesn't converge. Yeah, so the practical rule that you give it a value 100, 200, something, so that the program doesn't try indefinitely to converge. If it reaches 100, then the program stops. Looking at the results, yeah, then after that you can start looking at the results for different steps. At step 35, the deflection is at 56 millimeter, and you can see that the first few plastic hinges are becoming active. And then at the step number 70, just to pick up the steps, the deflection has increased, getting close to the level of deflection that we expect at the earthquake, which was order of 200 millimeter. And you can see more and more plastic hinges are becoming active nearly in the system. So again, continuing with the deformed shape, step 70, step 74, we are again very close to the anticipated deflection during the earthquake. And you can see that there are plastic hinges here. At step 78, we are almost 50% more than, or more, the target displacement was calculated to be 325. At the step 78, we have passed that value. So we don't need to do more than that or use the results beyond step 78. And at step 78, already we have a red plastic hinge, like all plastic hinges are active, and one of them has rotated beyond its limits. Step 79, this deflection is 632, and compression braces are getting close. Like two of them are at rupture. So that's what we have. So you see that in the design displacement, we have no rupture. Some plastic hinges have been created. That's what we designed for. We wanted plastic hinges to form, but we didn't want any rupture. So at design level, we are okay. And then when we go beyond design level, gradually we have ruptures. We can also have the program plotted or plug in the Excel, the say roof displacement versus base shear, which base shears are on vertical, the roof displacement on horizontal, which is the expected shape of the pushover curve. As I said, this could be used for design, but even the procedure up to here was very valuable. We saw that the plastic hinges were created at the locations that we wanted them. We saw that there was no rupture at the design level, or almost one after we reached to the target displacement. So we already have very valuable vision into our design, which is very valuable out in the design that you guys are performing or a structural engineer is performing. It's already super valuable. Some codes tell you how to use this curve to assess the earthquake load, which is more advanced than what we are doing here. So basically studying the pushover plot more closely, the base shear versus roof displacement. Stage one, up to some point, it's elastic or almost elastic. The design shear and the displacement at design value, they are also compared with each other. And then we have the design displacement. If I remember correctly, it was 200 millimeter plus. What is the real force when you are at the design displacement versus what if you had used completely elastic model, which would have skyrocketed. So that's the reason that we have the reduction factor. And then the target displacement. At target displacement, I mean, the structure has softened quite a bit, but there's no rupture. In fact, you need to go twice as much displacement until the structure really becomes unstable. And so they went through up to 600 millimeter until the structure really showed signs of collapse. So yeah, as I said, this is per se, just looking at this plot is very, very valuable for a structural engineer for his earthquake or her earthquake design. Examine the behavior of hinges. You can even do that independently, show hinge results on their display. You can look at the level of deflections in each hinge, hinges that were under compression and the hinges that were under tension. And you can monitor that rotation to see if it's reasonable. However, the code that we use, which was ASC 41, will mark the hinge as failed if the rotation is too much. So it's already built in, but you can also double check. So in summary, the structure was designed under effective seismic force procedure, and then the pushover analysis was used with the same pattern, but with varying the base shear intensity. Then we could really observe that there is a elastic displacement, the maximum elastic displacement, and the plastic hinges become active, and the structural behavior will become inelastic without necessarily collapsing. And the target displacement reach with tension braces yielding in tension, and the columns and beams remaining elastic. That's what we really want to see, that the members that we want to capacity protect, they remain elastic. So that's that's a very good observation and the value that we gain out of the pushover analysis. You can even create a model. So there's a second model where plastic hinges were added to the beams and columns. And you will see that some hinge forms in column in extreme displacement, not in the design level displacement or target displacement. Therefore, this is at 6, if I'm reading correctly, it's at 600 plus millimeter deflection, which means that our design is correct and all the beams and columns are capacity protected. All the plastic hinges really happen in the members in the seismic force assisting system, not anywhere else. That's it. I think this is valuable to you guys to practice through these models, make sure that they are available to you. And sorry, I walked you through this quickly and without being able to open the models. Send me your questions if you have any, but I think these are valuable. Now that you guys learn huge amount of material through the term, it is super valuable to be able to do a pushover analysis for your steel frame. And yeah, as we previously discussed, Friday, I'm on campus, and I'm there to listen to your talks, your side of what you learned and what you did for your project. That's it for today. I keep this open for any immediate questions, although I didn't really ask for the students to attend. Do we know where? Yes, sorry, Chinan, thank you for asking. I know that it is sent to me. I will email it to everyone. I don't have it on top of my mind. So yeah, we have determined it. So I will email it to you. It's in a different building, and I don't know all the buildings in the campus. Thanks a lot. Yeah, I will send it sooner rather than later, maybe today or tomorrow. I send an email with the location. Thanks a lot for people who are attending now and people who are listening later on. If there is no more questions, we can conclude this session. I can wait for about 1 more minute.